Okay, welcome to Let's Get to the Marks. Going through another organic A-level chemistry question. This one's about mass spectrometry and intermolecular forces. Let's get into it.
Chemistry.
Yeah, baby. Yeah.
The compounds in Table 2 all have a relative molecular mass of 58. Table 2 shows these compounds. We've got propanol. No, we've got propanol. We've got prop 2N1-ol. So the N stands for the double bond, the ol for the alcohol group. And we've got butane, 4 carbons. 4.1, explain why determining the precise relative molecular mass of propanol here and prop 2N1-ol here by mass spectrometry could not be used to distinguish between the samples of these two compounds. And the reason being they have the exact same number of atoms of each element. So they have the exact same molecular formula. They have the exact same number of atoms of each element. And guess what? They also have the same MR. So these are the two reasons why mass spectrometry is not going to work. Problem is with using mass spectrometry to try and distinguish between them, the M plus peak, remember that peak right near the end, the M plus peak that gives you the MR of the M plus fragment ion. It's going to be identical for both of them. It's going to be in the exact same place. Now, the question isn't saying how do you identify between them and can you use mass spec to distinguish between them? You could distinguish between these two compounds due to fragmentation patterns, but you couldn't distinguish between these compounds using the precise relative molecular mass because they both have the same molecular mass, they both have the same atoms and the same number of each element, basically C3H6O. So yeah, there we go. You're not going to be able to distinguish between them based on the mass spec alone by determining the precise relative molecular mass. Is not going to help you. You're going to need to use a fragmentation pattern. 4.2, the infrared spectrum of one of these compounds is shown in figure 4. Transmittance, we've got the wave number. Use the spectrum to identify the compound. State the bond that you used to identify the compound and give its wave number range. You should only consider absorptions with wave numbers greater than 1,500. They don't want us looking at any of these parts here. So what we're going to do, we're going to need to find a little data book, which is over here. Look what we find. 3,300 is going to be not that. Where is it? There, looks like that, an alcohol. Yeah, 3,300 is bang smack roughly in between 3,230, 3,550. So that is going to be a bond representing the alcohol. Now, we only find that bonds in prop 2N1-ol. Look, it's the only one with the OH group, so it's the only one of those isomers that could have made that pattern there because it has a peak at 3,300, which is the OH bond. So what I want to say is this is, oh gosh, prop. So we're looking at prop 2N1-ol. It's always long doing organics and putting all these hyphens in. Bond used to identify. So I looked at the OH bond. We could have looked at the double bond as it's the only one with a carbon-carbon double bond, the alkene bond. Wave number range of the bond, right? What was it? 3,230 to something like 3,230 to 3,550. I've got a brain like a sieve. It's like a listen. It's like a rice sieve. I can't even like, I've already forgotten what this was. I'm going to go 550. And if I've lost the mark, I've lost the mark because I've already forgotten what the range was. I think I might have to get my head checked. Okay. To get this, you probably need to, 2 of these will get you 1 mark and all 3 will get you all 2 marks. Yeah. Okay. Zinging, zinging, zinging. 4.3, predict the relative boiling points of these 3 compounds from the highest to the lowest boiling points. Justify this in terms of intermolecular forces. So let's just go in order, peeps. Which one has got the lowest boiling point? Well, the one with the lowest boiling point is going to be butane, and if you check this molecule, the only thing that you have between two butane molecules is weak van der Waals forces. Okay, temporary dipole-dipole forces formed by random movements of electrons. Covered that in other videos. Random movements of electrons create temporary dipoles, which are induced into the neighboring butane molecule, and then you get a weak force between the delta negative and delta positive. And so that is going to have the lowest boiling point. The second lowest boiling point is going to be propanal, which will be higher because propanal has this here. Have a look, see. Propanal has a polar bond, not it can't do hydrogen bonding because you need oxygen with nitrogen, fluorine, or hydrogen, and it's not bonded, it's bonded to carbon. But that is definitely more electronegative than the carbon and withdraws electrons, making that delta negative, delta positive, and we actually have a permanent dipole going on here, or dipole-dipole bonding. So that is going to have a higher boiling point because those are stronger than the weak intermolecular forces between butane molecules. And then lastly, but not least, in fact, the one with the highest boiling point is going to be prop-2n1ol. Why? Because it has an oxygen attached to a hydrogen. Now, if you have oxygen attached directly to a hydrogen, a fluorine, so if you have a hydrogen atom directly attached to an oxygen, a fluorine, or a nitrogen, you will engage with hydrogen bonding between adjacent molecules, and this will give you higher boiling points as it's the strongest intermolecular force. What we need to do is put that all down as an answer and smash out the 6 marks. Let's go. Okay, justify this. So we want to say butane has VDWS, van der Waals forces only. These are the weakest intermolecular force. Now, it doesn't ask me to explain it, and I won't get any marks for explaining it. So why am I going to do it? Well, it's for your benefit, really. So I'm just going to go through and explain how these weak temporary dipole-dipole forces actually appear. So these forces arrive due to three things. If it was a separate explanation for how do you get temporary dipole-dipole forces or van der Waals forces, you'd say random movement of electrons create a temporary dipole. Well, delta negative, delta positive on part of the molecule, which then induces a temporary dipole in a neighboring molecule. The key word there is to induce in the neighboring molecules because electrons repel other electrons. And this means we get weak intermolecular forces between delta negative and delta positive. So here's two butanes. One end becomes negative, the other positive, forcing the opposite end to go positive, that end negative due to repulsion of electrons. And then the third mark, we get a force between. But you don't get anything for that. So I'm just going to highlight what you would get the marks for, which is what I'm supposed to be doing in the mark scheme, right? So these forces are easy to break, easy to overcome because van der Waals forces are weak. So this is why it has the lowest boiling point. So technically, we just needed to say butane has only got van der Waals forces, which are the weakest intermolecular force. Therefore, not a lot of energy needed to break the forces, easy to overcome. Lowest boiling point. You need to say that it's the lowest. And then the second lowest boiling point, or the medium middle boiling point out of the three, is propanal. And why? Because propanal has a polar bond, which means it has permanent dipole-dipole forces. It doesn't have the temporary ones. The van der Waals force has got permanent ones. There's a permanent dipole there, not due to the random movement of electrons, but due to the difference in electronegativity between the oxygen and the carbon, the polar bond on, And then that has slightly stronger forces between the molecules, more energy to break, so it has a higher boiling point than butane. And then lastly, the prop-2n1ol, if I've got that right, is an alcohol. And alcohols contain the hydroxide bond, which is an OH bond. And if you have a hydrogen atom connected to either oxygen, nitrogen, or fluorine, the three most electronegative elements in the periodic table, you'll be able to do hydrogen bonding, which is the strongest of the intermolecular forces. Therefore, more energy needed to break. It has the highest boiling point. Whoo! Sharing's caring. Hit the like, punch up the bell, subscribe. Let's get to the marks.
You're still here? It's over.